Now that we ascertained the given distribution is actually a PDF, we can look at the properties. First of all, if you plot the PDF, and this is an actual plot, by the way, a precise plot, this is the famous, of course, bell curve. Okay, so this is what the distribution looks like. Of course, depending on the parameters that we will talk about later on, the shape of this bell curve might be wider, might be narrower, it might be larger, etc. But the shape is always the same. What about the statistics? Let's look at the mean of the standard Gaussian random variable. You just compute the integral x times the PDF here. Again, one small observation, but significant observation here is that this function is the PDF. The PDF function is an even function. You see, it's symmetric. Okay, so at minus x and x, you have the same value. It's a symmetrical function about the y-axis. Okay, that's an even function. When you multiply it with an odd function, which is x, you get an odd function, meaning that you get something like, which is symmetrical about the origin. Okay, so such functions, when you integrate them, the areas cancel each other out, as can be seen here. So the result will be 0. Okay, which is not surprising because you see this distribution is symmetrical about 0. Therefore, you expect the mean value to appear at 0, which it does. Next, let's look at the second moment. This is exactly equal to the variance because the first moment is 0 anyway. So you just compute this integral where you have the PDF here and you have x squared. And here, again, I'm not going to do it, but by integration by parts, using this configuration, you obtain this result. And this here, evaluated at infinity and minus infinity, you get the same result. Why? You have just x, which goes to infinity in either case, but also you also have e to the power minus x squared. So this is in the order of x over e to the power x squared. As x gets larger, e to the power x squared gets larger much faster than x. So this will go to 0, and that will be 0 for positive infinity, also 0 for negative infinity. So this term will be cancelled out, and we have a double negative here, so I can make them positives. But this expression here, again, you should recognize this directly as the Gaussian PDF. So integrate it over the entire real line, you should get from this term 1. So the variance is 1. You see, the mean is 0, the variance is 1. That is the reason we call this standard. Okay, a standard random variable, it doesn't have to be Gaussian. When I say a random variable is standard, what I mean is the expected value is 0 and the variance is 1. So the notation is given here. For a standard Gaussian random variable x, we show this with this n character and 0 and 1 here. So the first value here represents the mean, and the second value here represents the variance.